All right, welcome back to the physics videos. This is going to be an example of how to work out problems involving an inclined plane, but this time when there is friction. So I'm going to start with an inclined plane. Maybe I'll use the same angle. I have 30 degrees. I'm going to have something there that's sliding potentially down the inclined plane. In this case, it's going to have friction in addition to the force of gravity. The first thing I want to do is draw a free body diagram. So I'm going to have my box. I'm going to have the force of gravity pulling down. And then I'm going to have the normal force going perpendicular to the surface. And in addition, there will be a frictional force that's pulling in the reverse direction of motion, so it will be going up the hill. Remember, friction is always going to be reverse to motion. Let's see, I can give this a mass, but it won't matter, so I'll skip that. I am going to give it a coefficient of kinetic friction. So notice I'm going to start and assume that's already in motion. We can do another problem later if we want to figure out how to start it from a stop. But I'm starting in motion, so it's going to figure out how much acceleration there's going to be after it's already going in motion. You may recall the way we use friction. Our frictional force is going to be our coefficient of kinetic friction times the normal force. So thinking about how I want to tackle this, well, I want to figure out how much force is going to be going down the hill. I need to figure out what the force, the normal force is, and with that I should be able to add that up to find what the net force is. So my net force for this is going to be the force that's going down the hill minus the frictional force. So notice that fraction of gravity that's pulling down the hill is going to be going in the opposite direction to the frictional force. Okay, so let's see what I want to do. So I want to probably first separate out my gravity into the component parts. So remember how I do this. I'm going to turn my axes. I'm going to shift my paper around so that my x-axis lines up with the inclined plane, and my y-axis then lines up with the normal force. I'm going to have an angle here with the horizon that's going to be 30 degrees, which means that my angle inside this triangle is also going to be 30 degrees. So to blow this up, what I'm going to do is I'm going to separate my force of gravity. This is going to be in two components. One is going to be a force of gravity going in the y direction, but this is equal and opposite to the normal force. I don't care about direction, so I'll just use the magnitude of this for my normal force. Second component is now going to be going down the hill, and that's going to be my force down the hill that I want. My angle in here is going to be my 30 degrees that I started with. So now I can separate the components. I have to remember the sign is going to be my opposite over a hypotenuse. In this case, my force going down the hill divided by the force of gravity. I can solve this so that the force going down the hill is going to be the force of gravity times the sine of my angle. My cosine is going to be my normal force divided by the force of gravity. And I can solve this for the normal force. My normal force is going to be the force of gravity times the cosine of the angle that I'm interested in. So now I can go and figure out what my frictional force is and then plug that into my net force equation. My frictional force is going to be my coefficient of kinetic friction, mu sub k, times my normal force, which we just decided is the force of gravity times the cosine of my angle. So now I'm going to take my force, my net force. This is going to be the force going down the hill minus my frictional force, and I'm going to plug in what I know. Okay? So my net force now is going to be equal to my force going down the hill, which is force of gravity times the sine of the angle that I'm interested in. And I'm going to subtract from that my frictional force, which is this thing over here, the mu of k times the force of gravity times the cosine of theta. It's always a good idea to plug in, wait to plug in numbers, but to work out all the components that you can of a problem. In this case, we're going to get mass to cancel. So look at all those forces there. I'm going to plug in force equal to mass times acceleration. Right? So in this case, my net force is going to be mass times my net acceleration. Force of gravity is going to be my mass times my acceleration due to gravity times my sine of my angle. I'll subtract this from uk times my force of gravity again, which is going to be mass times acceleration due to gravity, times the cosine of my angle. You can see that my masses conveniently cancel out. So you do not need to know the mass to figure out the acceleration. Acceleration is just going to be the fractions of gravity that participate in this. So I can simplify this. My net acceleration is going to be acceleration due to gravity times the sine of theta minus mu k times the cosine of theta. I can't see a way to make this any simpler, so now I'm going to plug in some numbers. So I know acceleration due to gravity is going to be 9.81 meters per second squared. My sine of 30 degrees minus my coefficient of kinetic friction, 0.25, times the cosine of 30 degrees. Let's see, I'm going to end up with 9.81 meters per second squared times 0.2, I'll call it 9. And I'll end up with 2.7 meters per second squared as the acceleration that's going down the hill. So notice what we did. So very similar to an inclined plane without friction, but the only thing we've added in is our net force and our frictional force. We have the force of gravity is going in the y direction here is equal to the normal force. We use that to find the force of friction, and then we simplify it as much as we can before we plug any numbers in. I hope it helps.